In previous lecture, I already discussed reflexive relation and its properties. Today, I will discuss symmetric relation. Definition 4. A relation R on a set A is called symmetric if BA belongs to R whenever AB belongs to R. For all AB belongs to set A. So if BA present, then AB must be present. Then only it is symmetric. A relation R and a set A such that for all AB belongs to A, if AB belongs to R, BA belongs to R, then A must be equals to B is called as antisymmetric. If AB present, BA present in a relation, then A must be equals to B. If only AB present, it can be antisymmetric. If both AB, BA present, then A must be equals to B. If A is not equals to B, then AB and BA cannot be present in one relation. It's about antisymmetric. And in case of symmetric, if AB belongs to relation, then BA must be belongs to same relation. So we can say for all A, for all B, if AB belongs to relation, then BA also belongs to same relation. That's about symmetric. In case of antisymmetric, for all A, for all B, if AB belongs to R and BA belongs to R, then A equals to B. Just understand the difference between symmetric and antisymmetric. In case of symmetric, if AB belongs to R, then BA must be belongs to R. In case of antisymmetric, if both are present, AB and BA, then A must be equals to B. Let's see one example. Example 7. If A equals to ABC, then smallest symmetric and antisymmetric relation will be phi, or you can say empty set. Suppose one relation contains just BBCC. It is both symmetric and antisymmetric. Next, R3 contains AB, BA, BC, CB. This relation is symmetric, but it is not antisymmetric as A is not equals to B and B is not equals to C. So this relation is symmetric but not antisymmetric. Next, R4, that is A Cartesian product A, that is the largest symmetric relation. A relation is symmetric if and only A is related to B implies B is also related to A. And a relation is antisymmetric if and only if there are no pair of distinct element AB with A related to B and B related to A. So AB should not be distinct. If AB are equal, if A equals to B, then it can be. Means AB and BA both can belong to same relation. The terms symmetric and antisymmetric are not opposite. In some relation, you can see it is both symmetric and antisymmetric. Like here, empty set is both symmetric and antisymmetric. R2, it is both symmetric and antisymmetric. If AB present, then BA must be present. In this relation, just BB and CC. Just diagonal pair are present. As AB is not present, so BA is not required. It is symmetric. Also, it is antisymmetric. Now, number of symmetric relation possible, it is 2 power n multiplication n plus 1 divide 2. We are just multiplying number of diagonal relation and non-diagonal relation. Diagonal relation means AA, BB, CC. These are the diagonal pair. So a set having n elements, number of symmetric relations possible with diagonal pair equals to 2 power n and with non-diagonal pair equals to 2 power n multiplication n minus 1 divide 2. Now we'll multiply these two. So 2 power n multiplication 2 power n multiplication n minus 1 divide 2. It will be 2 power n square plus n divide 2. That we can write as 2 power n multiplication n plus 1 divide 2. So number of symmetric relation possible equals to 2 power n square plus n divide 2. Let's see one example. Which of the relation from example 5 are symmetric and which are antisymmetric? Same example I used for reflexive relation. There are some relation we need to identify which one is symmetric and which one is antisymmetric. R1, it is neither symmetric nor antisymmetric. I just see here 1, 2 present, 2, 1 present. Then 3, 4 is present, 4, 3 is absent. 4, 1 is present, 1, 4 is absent. So this is not symmetric and this is not antisymmetric also, as there is a pair present 1, 2, 2, 1 and 1 is not equals to 2. So not antisymmetric. Is it reflexive? Here 1, 1 present, 2, 2 present, 4, 4 present, but not 3, 3. So not reflexive. Now relation 2, it contains 1, 1, 1, 2, 2, 1. 1, 2, 2, 1 present, so it is symmetric. It is not antisymmetric and it is not reflexive, as all diagonal pair are not present. Next relation 3, 1, 1, 2, 2, 3, 3, 4, 4. So it is reflexive. Then 1, 2 present, 2, 1 present, 1, 4 present, 4, 1 present. So it is symmetric, but it is not antisymmetric, as 1 is not equals to 2, 1 is not equals to 4. So R3 is reflexive and symmetric but not antisymmetric. So we found R2, R3 are symmetric because in each case BA belongs to relation where AB does. It contains both AB and BA order pair. Now relation 4, relation 5 and relation 6. Relation 4, 2, 1, no 1, 2, 3, 1, no 1, 3, 3, 2, no 2, 3, 4, 1, no 1, 4. It is not symmetric. It is antisymmetric. So whenever there is a order pair like AB, BA is not present. So it is antisymmetric but it is not reflexive. So this relation R4 is not symmetric, not reflexive, but it is antisymmetric. Now R5, it contains 1, 1, 2, 2, 3, 3, 4, 4. So it is reflexive. Now 1, 2, no 2, 1. 1, 3, no 3, 1. 1, 4, no 4, 1. 2, 4, no 4, 2. 2, 3, no 3, 2. 3, 4, no 4, 3. So it is antisymmetric but not symmetric. Now R6, it contains just 3, 4. It is antisymmetric, not reflexive and not symmetric. So we found R4, R5 and R6 are all antisymmetric. For each of these relations, there are no pair of element A and B such that AB and BA both belongs to the same relation. That's why these three are antisymmetric. R2, R3 are symmetric. R1 is neither symmetric nor antisymmetric nor reflexive. Now next example, example 9. Which of the relation from example 6 are symmetric and which are antisymmetric? I already discussed example 6 for reflexive relation. Now I will check which one is symmetric and which one is antisymmetric. These are the relation. We have 6 relation. Now R3, R4 and R6 are symmetric. In R3, A equals to B or A equals to minus B. So B can be equals to A or B can be equals to minus A. So there can be order pair AB, BA such that A equals to B or A equals to minus B. So R3 is symmetric. Next R4, A equals to B. So B can be equals to A, that's why it is symmetric. Next R6, A plus B less than equals to 3. There can be B plus A less than equals to 3. Suppose A equals to 1, B equals to 2. So 1 plus 2 less than equals to 3. Then 2 plus 1 less than equals to 3. So 1, 2 can be an order pair. Now which relation are antisymmetric? The relation R1, R2, R4 and R5 are antisymmetric. Now R1, if A less than equals to B, then B less than equals to A means A equals to B, right? So R1 can be antisymmetric. Next R2, A greater than B, but it's impossible that B is greater than A. So if A be present, then BA cannot be present. So it is antisymmetric. Next R4, if A equals to B, if AB relation present, then BA relation can be present and A equals to B. So R4 is both symmetric as well as antisymmetric. Next R5, A equals to B plus 1, so it is impossible that B equals to A plus 1. So if A be one order pair present, then BA is impossible. So that's why R5 is antisymmetric. If A be present and BA present, then A must be equals to B, then it is antisymmetric. If A be present and BA existence is impossible, then it is antisymmetric. Now example 10, is the divide relation symmetric or antisymmetric? The divide relation is not symmetric, as if 2 divide 1, then 1 not divide 2. So if 6 divide 3, then 3 doesn't divide 6. This is not possible. So that's why it is not symmetric. If A, B are order pair and A divide B, that doesn't mean B divides A. It is not symmetric, but it can be antisymmetric. If A divides B, B divides A, then A equals to B. Else, if A be present, then BA is impossible. So the divide relation is antisymmetric but not symmetric. In today's lecture, I discussed symmetric and antisymmetric with some examples. In next lecture, I will discuss transitive relation. If this lecture is helpful for you, please like, share and subscribe. Thank you.